Hello, everyone. My name is Jacob Wagner, and I'm going to be presenting the paper Model Learning and Predictive Control for Autonomous Obstacle Reduction via Bulldozing. This work was supported by the Engineer Research and Development Center, Construction Engineering Research Laboratory. This research is motivated by the needs of Army combat engineers who perform a variety of construction and demolition tasks, often using large construction equipment such as bulldozers. This is a dangerous job as combat engineers work in contested areas where they are the target of enemy fire. Teleoperation can reduce the risk to equipment operators. However, it may not be possible when communications are being actively denied, which is why the U.S. Army is interested in developing robotic equipment capable of performing engineer operations such as obstacle reduction autonomously. Specifically, we focus on the task of earth and berm removal, an example of which is shown in the photo. The goal of this work is to investigate the feasibility of using high-dimensional model learning methods to model the complex interaction of a bulldozer blade with soil, and secondly, to determine if the learned models are accurate enough to enable removal of an earthen obstacle using predictive control. We have developed a simulation of a bladed vehicle using Vortex Studio, which models both multi-body dynamics and soil tool interaction using an efficient hybrid particle and mesh-based representation of soil, enabling real-time simulation at 60 Hz. We use a simplified vehicle model consisting of a free-floating blade capable of moving in 2 dimensions, longitudinally and vertically. As the blade is not attached to an actual vehicle that is resting on the ground, the velocity of the blade is controlled via a constraint, which exerts a force on the blade proportional to the velocity error. The force is limited to emulate maximum pushing forces as on real machines. The terrain is randomly generated using a mixture of Gaussians, and a 1 meter tall berm is in place for the system to remove. The goal of the system is to move the excess soil out of the rectangular region of interest in order to achieve the terrain height prior to the berm emplacement, or PGZ. The system state includes a height map covering a 6 by 10 meter area centered on the current blade position, where height map values are relative to the height of the blade. The blade position and velocity are also included in the state. The blade velocity in the longitudinal and vertical directions can be controlled by the system. We developed 2 different approaches to learning a forward model of the earth-moving process. Dynamic mode decomposition with control, or DMDC, is a method for learning reduced order models of nonlinear dynamical systems using only measurements of the state and control over time. DMD is particularly well suited to problems where the state encodes a spatial distribution of values. The second approach we investigate is based on the world models architecture and is depicted in the figure below. The model is composed of 2 networks. A variational autoencoder, or VAE, reduces the dimensionality of the height map observation H to a latent state Z, and a mixture density network, recurrent neural network, or MDN-RNN, predicts the evolution of Z over time. The VAE decoder can be used to turn a predicted latent state into the predicted height map. To train the models, we collect a small data set consisting of 252 separate 2¼ second long trials where a human controls the simulated blade. This data set is separated into approximately 6 minutes of training data and 4 minutes of test data. After training, the models are used to produce 2-second predictions, and the mean average error of the predictions are computed for the height map as seen in the top row, the blade position in the middle, and the blade velocity in the bottom. DMDC does marginally better than world models on the height map predictions. However, it performs much worse than world models at predicting the blade position and velocity. This figure provides a more qualitative comparison of the methods. Visualizing the predictions for a representative episode, the top figures displays the predicted height maps for steps 7, 67, and 127 of the episode, where prediction begins at step 7. The lower plots show both the position and velocity predictions as dashed lines and with the true state as solid lines. Both the models show the berms being cut into and the soil being pushed in the positive longitudinal direction. DMDC predicts less blade movement than is actually observed, while world models much more accurately predicts the change in position. Looking at the position and velocity predictions, we can see that world models are doing a much better job, especially for the longitudinal components. After the models are learned, we are interested in using them to enable our vehicle to remove earthen berms. We formulate obstacle reduction as an MPC problem solved via moving horizon-based optimization. Instead of directly optimizing for the action at each step, we define a 2D template action trajectory motivated by the human operators and parameterized by 2 accelerations. This helps to reduce the size of the search space significantly, enabling the use of simple grid search for optimization. To further reduce the computational burden, optimization is performed only every 10 simulation steps. Occasionally, this controller produces actions that bury the blade in the soil or raise the blade well above the terrain. We implement recovery behaviors that are engaged temporarily to help the system resume normal operation. We evaluate the performance of both the DMDC-based controller and the world models-based controller on a berm removal task as compared to the human operator baseline. With the use of recovery behaviors, DMDC slightly outperforms world models and performs similarly to the human operator. However, when recovery behaviors are disabled, DMDC performance decreases significantly, while world models only performs marginally worse. As can be seen in this video, the DMDC-based controller consistently produces commands to drive the blade into the ground where the blade becomes stuck, and the recovery controller is needed to dislodge the blade. The world models controller, on the other hand, will often raise the blade after becoming stuck for a short period of time. However, we believe this approach shows promise. For earth-moving equipment, which are challenging to accurately simulate and are difficult to obtain large quantities of real-world training data on safely, this data-efficient model learning and MPC approach hints at a way learning-based control can be used to accomplish more complex autonomous earth-moving tasks.